Hello guys, and welcome back to another video within the Unit 1 of the iGCSE syllabus. Unit 1 is all about data representation, and so far we've looked at binary, the fundamentals of it, how we convert in different number systems, and today we've got a nice easy lesson looking at what we call character sets and how characters are represented in the computer, which is fairly simple to follow. So we're over halfway through Unit 1 of the syllabus, and there's only a few more lessons left to do with data representation, starting with text. So straight from the syllabus, we are required to understand how and why computers represent text and use what we call character sets, including this term ASCII and also Unicode. So we're going to look at how these two systems represent characters in the computer. So like we've mentioned this far, guys, we've said that computers only understand ones and zeros due to the fact that this is electricity for on and off. So any data that travels around the computer is in a series of ons and offs, or as we now know, binary numbers. So what that means is that everything that we see as a human, including text, music, images, videos, and basically everything that we see and do on a computer needs to be translated into binary numbers in some kind of system. So to start us off, we're going to start with letters and symbols, and essentially everything you can see on a keyboard, and how this data is converted into binary so that the computer can use and understand it. So the way we can think of it is every time we press a keyboard key, a series of ons and offs are sent down the cable into the computer, where the CPU will then process these ons and offs and convert it into some kind of character. So for example, if you press down on the letter M on your keyboard, down the cable of the keyboard wire or through Bluetooth if it's wireless, will go a 01001101. And the computer will receive this as a number and convert it into the letter M. Now, obviously we can convert this into denary, but what the computer will do is instantly do it and then work out that this is the letter M and then display it on your screen. The same thing applies if you press the virtual keyboard on your touchscreen phone or your tablet, but all characters need a numerical value so that we can convert it into binary. So before we figure that out, let's just look at what's on the keyboard so far. We've got 26 letters, which can all be uppercase and lowercase. We've also got 10 numbers that need to be represented and approximately 36 symbols, which gives us a total of 98 different characters. In order to store 98 different values, we'd only need technically, let's just draw our binary chart again. To make 98, we need a 64, a 32, and a 2. So technically, we only actually need 7 bits. Okay, 7 bits is more than enough to store all of the characters that you can see here. So all of these different numbers that can be stored in 7 bits will be assigned to each of the keyboard letters, including the numbers themselves. All these different buttons on the keyboard will have a different numerical value, which is then represented in binary. Okay, so the letters will have a number, the characters will have a number, the numbers will have their own number, and all these numbers go into binary and the computer can understand what they are. Now, obviously there needs to be some kind of reference to what these numbers equal in the computer. And this is where ASCII comes in. So the American Standard Code for Information Interchange is one of the first rules set up in order for computers to understand letters and characters and even numbers. In the table below, we can see conversions of the letters into denary and obviously binary. So if we go in here and we can see an exclamation mark is decimal 33. Now in a computer, that will see it as this. So when you press an exclamation mark on your keyboard, down the wire or through Bluetooth will go this binary number and on the screen will pop an exclamation mark. And the same thing applies for all the characters that you can see on a keyboard. As you can see, all the characters have an equivalent binary value, and that is how the computer understands what they are. So obviously the Americans developed this as they use the 26 letters that we discussed in the alphabet. They've also got the general characters what are used in terms of symbols. And once this system is developed, the communication systems around the world that used computers were able to communicate via a digital platform because we had a rule for how these letters and characters will be represented. So for example, if the Americans were communicating with the UK, even in 1963, they had a copper cable under the Atlantic Ocean, and down this copper cable would have went a series of zeros and ones to represent these characters in the table. Now, as we can see, ASCII uses 8 bits. And we know that if you add up all of the 8 bits in our conversion table, you're given the number 255. But as we've discussed in previous lessons, the actual number of values is 255 because we have 0 to 255. Okay, so we've got 256 unique values. That means we can store 256 unique different characters or symbols or even numbers. So ASCII uses 8 bits, okay, and it's enough to store what we can see on the screen. Obviously, this table goes further down and the alphabet will be continued. But as we've discussed, 256 unique values for what the Americans would use in their alphabet. So with 256 unique values, hopefully you are starting to figure out what's going to happen as we move forward. Like we said, this was from 1963. This system was developed over 50 years ago. So moving forward in time, what do we think would have happened in terms of technology and the way the world communicated? And obviously with the use of computers, ASCII is not going to be enough. 256 characters would not be enough to store alphabets from, yet you've got it around the world. And this is where Unicode came in. Okay, so Unicode is a universal standard. So if we take the uni from Unicode, okay, this means universal. So universal means across the globe. So the universal standard became Unicode so that everybody across the world was able to communicate. If the whole world agreed on the same standards of communication, then everyone would then be able to communicate via computers. So the Unicode standard was supported by most operating systems and most web browsers, so that different countries around the world could then communicate using binary numbers. And as you can see here, we've got a character map, we've got much more symbols. We can start to see accents from different countries around the world, different letters from different alphabets. We've also got different symbols and currencies. Basically, we were able to store more characters from different languages. But then we've got to think, how were we able to do that? Obviously, we need bigger numbers. And that's what Unicode did. Okay, it's a new code allowing for many more characters. The first Unicode that was developed used 16 bits rather than 8 that ASCII used. So as you can imagine, 8 was no longer enough. But by simply doubling the amount of bits to 16, we were then able to store 65,000 possible combinations. We could have 65,536 unique values to assign to different alphabets from around the world, different symbols, different characters. And obviously, the whole world was then able to communicate. In fact, there's a 32-bit version of Unicode which is used today, and there's over 4 billion possible combinations, which is more than enough to store all the characters and languages from across the world. In fact, with 4 billion possible combinations, it wasn't just characters from a keyboard, it was what we see today in terms of emojis. Emojis also use Unicode. When you click one of these smiley faces on your keyboard, there's actually a binary representation for each of these emojis. And as we know, the amount of emojis that we have access to each year grows and grows. And just out of interest, the term emoji, E is Japanese for a picture, and moji is Japanese for a character. So a picture character. And as we know, emojis are the typical standard of communication in today's world. And that's pretty much it for character sets, guys. Okay, so a nice, easy lesson to follow. We've got some questions here just to wrap up. And by all means, if you want to give the video a pause and give these questions a go, do so. And I'll go over the solutions shortly. So how many bits are in extended ASCII? Well, I didn't specifically mention extended ASCII. The original ASCII was 7 bits, and then extended ASCII was 8 bits, which allows for 256 values from 0 to 255. So how many characters does this allow for? Well, 256 different characters in extended ASCII, which uses 8 bits. How many bytes are in Unicode? Well, we said 16 bits, which equals 2 bytes. Or even the modern standard of Unicode, we've got 4 bytes, which allow for 4 billion different values. A typical question that you see in the computer science exam is asking you to work out what a letter might be, given an ASCII code of another character. Now, you're never going to be required to remember the whole ASCII alphabet, but what you do have to do is show some knowledge that if F equal to 102 in the ASCII system, then what would G be? And all you have to do is figure out that G comes after F in the alphabet by one place, literally E, F, G. So if F is 102, then G must be 103. This is a typical question, guys, so please be aware. And you may even be required to work out a couple of spaces in the alphabet. For example, if F is 102, then what is H or even I? And then you just have to go along the alphabet, work out how many values it's gone up. So if it's 104, 105, etc. You're never required to remember any of the values. They will give you one to start with, and then you have to figure out what the subsequent value might be. Finally, how many bytes are needed to store hello everyone? As we mentioned in one of the first slides, one character takes up 7 bits or a byte. So how many bytes would it be? Well, it's 1 byte per character, 1 byte per character. And here we have 1, 2, 3, 4, 5. The space is an actual character as well, so please bear that in mind. Then we've got 7, 8, 9, 10, 11, 12, 13, 14. So 14 bytes to store the 2 words hello everyone with a space in between. And just to finalize, here's our solutions. 8 bits for extended ASCII. How many characters? 256. How many bytes are in Unicode? Well, 16-bit Unicode has 2 bytes and 32-bit has 4 bytes. If F has the ASCII code 102, whereas the ASCII code for G, it's 1 more in the alphabet, so So 1 plus 102 is 103. And then how many bytes are needed to store hello everyone? 14 characters equals 14 bytes. Remember, the space counts in between hello everyone. Next lesson, we are looking at digital audio. So how we represent sound in the computer. And we'll look at the process of how we convert sound waves into a digital format, i.e. binary numbers. So hopefully you've enjoyed today's lesson, and I will see you next time.